Okay, so welcome back everybody, and this morning I'm going to focus on hybrid programming with MPI and OpenMP together in the same application. So I'll start off with a bit of motivation about why you want to do this and what the potential gains are. And then as well, focus on the good side to begin with. So what are the potential advantages of using MPI and OpenMP, and why you might want to do it. And then I'll sort of go on to talk about what are some of the problems and issues that you might face when doing it. And then I'll go through the different possible styles of MPI and OpenMP program, discuss their relative disadvantages, and in the course of that I'll be talking about MPI's thread interface a little bit. Okay, so same as last time, please feel free to ask questions as we go along. If you type in the chat, then I'll keep an eye on that and try and answer any of your questions. I'll also stop in a few places and ask specifically. Okay, so what's the motivation here? Oh, well, clearly with the now that everything is multi-core chips, and these days very large core counts coming on chips, all the sort of current CPU systems that we're likely to come across are these clustered architectures. They're distributed memory systems where each node consists of a shared memory multiprocessor. So we have this hybrid hardware where we have a single address space available within each node, but separate nodes have separate address spaces. So the question is, well, how should we program such a machine? Well, in general, it's absolutely fine to use MPI across the whole system and essentially ignore the fact from a programming point of view that we have the single address space inside a node. Unfortunately, we can't in general use OpenMP or any other thread-based API across the whole system, because that requires a support for the single address space. It's not completely impossible. It's doable in software, so you can basically have a special operating system that implements a single address space across multiple nodes, but it's really inefficient. It's also possible to do it in hardware, but it's very expensive. So these systems were more popular in the past. Don't seem to see very many of them around today. But things like the SGI Origin machines supported a single address space over up to about 1,000 cores or so in hardware, and you could run OpenMP across 1,000 cores if you chose to. But we don't tend to see many of those systems around these days. The other possibility is we could use OpenMP or other threading interface inside a node, and then use MPI to communicate between nodes. But the question is there any advantage to doing that? Well, the answer is maybe, but we have to have some realistic expectations here. It's not a magic bullet, and in general, MPI and OpenMP together does not improve performance, and may actually make it worse if we're in the regime where the MPI application is still scaling well. So if your MPI application MPI code is scaling fine up to the number of cores that you're interested in running on, then there's likely to be very little advantage in going hybrid. The benefits tend to come when the MPI scalability, and that can be either in execution time or in memory, starts to run out. And it's maybe possible that the hybrid code can extend the scalability to larger core counts. So the best you can really hope for is performance curve like something that looks something like this. So what I'm sort of plotting here is kind of an imaginary plot of high is good here, and of course it's running on. And the red line is perhaps illustrative of what you would get from a typical MPI code. To begin with, it starts off scaling well, almost linearly, but then eventually the scalability diminishes, reaches a maximum somewhere, and then going beyond that, the performance will start to decline as the overheads of parallelism start to dominate. So what you often find with, or what you can probably, the best that you can really hope for from an MPI and OpenMP solution is that it may well perform a bit worse at low core counts where the MPI code is still scaling very well. But as we go to higher number of cores, it maintains its scaling behavior for longer, and that the peak performance occurs higher than the pure MPI code, and also further to the right with larger numbers of cores. So that's the kind of behavior that you are probably going to get from a well implemented MPI plus OpenMP solution. Of course, it's possible to just have disaster, and if things don't go well, then it's entirely possible that the blue line just always lies below the red line somewhere, and that you don't gain anything at all. So what are the potential advantages? Well, I'll talk through these in each in a bit more detail, but the main ones that we can get out of a hybrid code are, first of all, reducing memory usage. That's actually a very important one. So it's not directly related to performance necessarily. We may be able to exploit some additional levels of parallelism to extend the scalability of the application. We may be able to reduce load imbalance, to do a better job of balancing load. And then finally, we also might be able to reduce some communication costs. So let's look at reducing memory usage to begin with. So the kind of most obvious case here is some MPI codes use some sort of replicated data strategy. So what that means is that all the processes have some copy of a major data structure. And even classical domain decomposition codes have a certain amount of replication in the halos. So you add these halo cells around your local domain, which hold copies of cells which really belong to other processes. So there's even in those cases, there's still some data replication going on. There's also memory usage internal to MPI. So MPI's message buffers can also consume quite significant amounts of memory sometimes. particularly if you're sending large messages and if processes tend to communicate with large numbers of other processes. So whenever we have copied or replicated data, a pure MPI code obviously needs a copy per process, and then by implication, a copy per core. Whereas in principle, a mixed MPI and OpenMP code would only require one copy per node. Okay, and the data structure can be shared by multiple threads within a process. And then that also may reduce the MPI internal memory usage, because the MPI no longer needs buffers for messages that are going inside the node, because that communication is replaced by reads and writes to shared memory by threads. So this is possibly going to become increasingly important. I think so recent trends suggest that in large HPC systems, the amount of memory per core is not really changing very much. Okay, so we get, although we're getting larger core counts and larger amounts of memory attached, then the total amount of memory per core is kind of staying roughly the same. It's sort of 1 to 4 gigabytes per core. That's that kind of order, and that hasn't really changed very much in the last, I guess, last decade or so. Really, that's we've kind of been stuck with that. And it's technically possible to put an awful lot more memory in a node. It's just expensive and consumes a lot of power. So there's design of large HPC systems is often a compromise to have enough memory for most applications, but not so much as to consume too much power or cost too much in the first place. There is also an effect of domain size on Halo storage as well. So if you think, if you do basically a strong scaling type experiment, or that's your usage of a machine is really strong scaling, so that you're basically trying to solve the same global problem size faster by using more and more processors. Then typically, if we use more processors, then we will shrink the local domain size. And there are some problems which will genuinely weak scale. That's possible, but not a lot of applications behave like that or tend to get used like that. Okay, what's Clement saying? Yeah, also, yeah, bandwidth to memory is also a problem. Yeah, absolutely. And so a lot of modern hardware is for scientific application. We're very much constrained by memory bandwidth. I guess what I'm really focusing on here is just on memory capacity. Does your problem actually fit in memory or not? But the bandwidth issue is a good point, but it's not typically something where hybrid programming really helps an awful lot, I would say. So if you think what happens when we decrease the local domain size, then the amount of Halo data also decreases, but eventually it starts to occupy a significant fraction of the storage. And that's even worse if we have deep halos. So if we have halos that are more than one grid cell deep, or we have problems like quantum chromodynamics where you're working in more than 3 dimensions. But just to illustrate, suppose that if you think about a domain decomposition where the local domain size is has 50 cubed, so it's a 3-dimensional domain which is 50 by 50 cells, then the halos occupy about 11% of the memory associated with that. So by adding the halo cells in each dimension, you increase the memory usage by about 11%. Then as you come down to 20 cubed, that goes up to 25%. And then by the time you get down to 10 cubed local domain size, then your halos occupy almost half the memory. So memory usage is an important motivator for hybrid code, but there are also potential performance gains to be had. So turns out that some MPI codes don't scale beyond a certain core count because essentially they run out of available parallelism at the top level, or at the level at which the MPI application is actually exploiting parallelism. But there might be some additional lower levels of parallelism that can be exploited. So in principle, we could also exploit those low levels of parallelism using MPI as well. But in practice, that can be hard. The low level parallelism may be less regular, may be harder to load balance. It might have some irregular or runtime determined communication patterns, which are sort of thing that's hard to deal with in MPI. I mean, it's not impossible, it's just a lot of software engineering effort. But more commonly, it may just be really a lot of effort to work around the design decisions in the original MPI version. It may be an awful lot of work to take the MPI implementation apart and rebuild it so that it's able to exploit more than one level of parallelism. So for practical reasons, it may well be easier to try and exploit those additional levels of parallelism using OpenMP threads. And there's several advantages to that. I mean, one of them is just the kind of ease of use of OpenMP in some sense, because we can take an incremental approach to adding OpenMP, which may not give you the very best performance, but it's relatively tractable in terms of development cost. And obviously the OpenMP parallelism can't extend beyond a single node, but that might be enough, especially if we're seeing nodes with like ARCHER2 is 128 cores per node, then that's quite a lot of parallelism. It's often not sensible to run one OpenMP. One process with 128 OpenMP threads on this hardware, but in principle, there's increasing amounts of parallelism available inside a node. So if you look at what's happening to modern HPC systems, then you see that they are getting more powerful. But what's happening is that we're getting more cores per node. But the total number of nodes isn't really changing that much. Next possible advantage is reducing load imbalance, and that's because load balancing between MPI processes can be difficult. And the reason for that is because of the programming model. We need, in order to balance load in MPI, we need to be able to transfer both the computational tasks and the data associated with them from overload underloaded processes. And that means that transferring small tasks may not be very beneficial. It also means that if we try to scale up to very large numbers of processes, then having a global view of loads may not scale very well. So it may not be possible to really have for any one process to have a global view of the load on all the MPI process, all the other MPI processes. So we may need to do something that's less optimal. So, for example, to restrict ourselves to only transferring loads between neighbors. So that's reduces the capability of the load balancing system. On the other hand, load balancing between threads is much easier. We only need to transfer tasks and not the data. The data does have to move. That's all implicit, and the overheads are lower, so some fine-grained balancing is possible, and it's much easier to do dynamic load balancing with threads than it is with MPI, and it's also trivial to have or fairly trivial to have a global view of the load on every thread. So what that means is that for applications that have load balance problems, keeping the number of MPI processes small or smaller can be an advantage. It's maybe okay to balance the load off over 1,000 MPI processes, but if we try to do it over 10,000 or 100,000, then it becomes difficult. And then the final possible advantage is to do with reducing communication costs. Okay, so it's natural. This might be the first thing you think of as being the first benefit you might think of as doing hybrid code, because you think, well, it's communicating data inside a node is faster between OpenMP threads than between MPI processes. Because there's none of the stuff that MPI has to do, like copying into buffers. There's no overheads of calling into the MPI library, and that is true. But there are lots of caveats, which I'll come back to later. In practice, the real benefit often comes from the fact that some MPI codes communicate more data than is actually required to satisfy the data dependencies in the application. And this typically occurs where the data dependencies are irregular or data dependent. And it's just for convenience. It makes the MPI implementation a lot easier if you always just send to your neighboring process everything that it might need in the next time step, for example, rather than actually trying to reduce it to only the data items that it's really going to use in the next time step. So there are some circumstances where collective communications can be improved using MPI and OpenMP. So particularly collectives like all-reduce or all-to-all. In principle, the MPI implementations are pretty well optimized for clustered architectures. It's not always the case. Sometimes it also requires a bit of you can do stuff to tune the MPI collective implementation. There's often settings you can choose. Possibly you can choose between different collective algorithms as well. They aren't always as well optimized as for a particular piece of hardware as you might suppose. But there are cases where we're optimizing for for these clustered architectures is hard to do. So for example, all-to-all V is difficult because that's where every MPI process is sending a different amount of data to every other process. So optimizing that for shared memory nodes is actually quite difficult. Because a single MPI process doesn't have all the information it needs. And there also can be cases where the hybrid version transfers less or communicates less data around. For example, in all reduced, it might be true that every thread contributes to the sum, but in the end, only the master threads in every process actually need the resolve. So there's a part of the all reduce which would be in principle one core on every node, then distributing the results to all the other cores. That stage of the all reduce operation isn't actually required we have a higher where So I just want to give an example of this this notion where MPI codes communicate more data than they really need. And this is the European Centre for Medium Range Weather Forecasting's weather forecasting code, which is called IFS. I think it stands for Integrated Forecast System, something like that. Anyway, it's their main weather and climate code. And they use a numerical method which is called semi-Lagrangian advection. So don't worry if you don't know what that means. But basically, what it means is that basically it's solving the fluid flow in a way that requires data from neighboring grid points, but only in an upwind direction. Okay, so only actually need data from things like flow velocities and temperature and humidity. Only need to communicate those to neighboring grid points in the direction that the wind's actually blowing. But that knowledge is difficult to exploit in MPI. So the MPI solution is just to communicate all the data to the neighboring processes that could possibly be needed, because a given process does not know what the wind direction is on the grid point on its neighboring process. On the other hand, if we have an MPI and OpenMP solution, then if we're within a node, then we only read data from other threads' grid points if it's actually required. Okay, so that it's easy in OpenMP just to say, okay, I need data from certain grid points that belong to other threads, but I'll just go ahead and read them. That's no problem. So it actually turns out to be a significant reduction in communication costs. Yeah, so kind of schematically, it looks something like this. Okay, so imagine here a part of the grid. So this is a two-dimensional grid that covers the surface of the Earth, and each one of the boxes is the local domain for a different MPI process, say, and the current wind flow in the middle process is shown by the red arrows. Then the data that it actually needs for the next time step is might only be the green grid points, which belong to other processes. But the MPI solution will actually not only communicate the green grid points, it'll communicate all the purple ones as well, despite the fact that data is not required by the process in the middle. So by going to a hybrid solution, if now these are if these subdomains are owned by threads rather than processes, then the thread processing the thread computing the middle domain here can just go and read go and read the green values and not touch the purple ones at all. Okay, good. Any questions so far? Okay, so now I want to focus for a bit on what are the problems. So it's not necessarily a sensible or easy thing to do to go from pure MPI to MPI and OpenMP. So what are the potential downsides? First of all, let's think about the software engineering aspects. In most cases, the development might be harder than it is for a pure MPI code. So, as you're well aware, probably MPI programming is in general somewhat easier than MPI, but it's still parallel programming. It's still hard, and your application developers need yet another skill set. And as you're also well aware, OpenMP is subject to subtle race conditions, non-deterministic bugs, which means that correctness testing is quite tricky. So in terms of portability, it's not really a bad story at all. Both OpenMP and MPI themselves highly portable. Not absolutely perfect, of course, but pretty good. Combined MPI and OpenMP is slightly less so. The main issue here is the thread safety of the MPI library, so which we'll talk about in more detail later on. But if the maximum amount of thread safety is assumed, then it's possible that portability will be reduced because not all MPI implementations may necessarily support that or support it very well. It's from a software engineering point, it's probably desirable to make sure that your code functions correctly, possibly with some conditional compilation as a standalone MPI code. And possibly as a standalone OpenMP code as well, though that's maybe less useful. Okay, so libraries can be quite a problem. So in particular, if your pure MPI code uses some distributed memory library, then we're going to need to replace that with a hybrid version. And that may or may not exist. If the pure MPI code uses a sequential library, then we may need to replace that either with a threaded version of the library, which is called from the OpenMP master thread, or alternatively, possibly with a thread-safe version of the library that's called from inside OpenMP parallel regions. And again, it's maybe possible that neither of those things exist. That you have that there's a sequential library where no threaded version exists, and neither does a thread-safe version. There's another potential problem here, is that if the threaded or hybrid library versions use something other than OpenMP threads internally, then we can end up getting problems with thread oversubscription. What can happen is that both your application, which is creating OpenMP threads, and the library, which is creating some other threads which are not under control of the OpenMP runtime, those two sets of threads might not idle nicely when they're not being used. So, you may be switching from places in your application code where you're running OpenMP parallel regions to places in your code where the OpenMP master thread is making a call into a multi-threaded library. So you're switching back and forth between using two actually underlying different sets of threads, and that doesn't always work well. It depends a bit on the compiler, and depends on the OpenMP implementation, and whatever else is being used, whether that works okay. And then there are a bunch of performance pitfalls that we can fall into. As we saw last time, adding OpenMP may introduce some additional overheads which weren't present in the MPI code. So things like OpenMP barriers, for example, fault sharing, sequential sections, numer effects. All things which we talked about last time. And there's also some added complexity, because adding OpenMP introduces a tunable parameter into how we run the code. So this is the choice of the number of threads per MPI process. And the optimal value of that will depend on the hardware that you're running on. It may depend on the compiler that you're using. Depend on the MPI implementation that you're using, and it'll also depend on the input data as well. So maybe just the size, depending on the size of your problem, the optimal value of the number of threads per process might change. And so in general, it's pretty hard to guess the right value, the optimum value, without doing some experiments. And then also the placement of MPI processes and their associated OpenMP threads within a node can have performance consequences. By and large, if we're running a pure MPI code, then we don't really care which core a given MPI process is running on within a node. Okay, it usually makes very little difference how the MPI processes are bound to cores within a node. But once we get to hybrid, then it does matter. Okay, particularly with NUMA architectures, it's important that all the OpenMP threads that belong to the same process are running in the same NUMA domain or on the same socket, for example. Okay. What other things do we have to worry about? Well, if we just take a fairly simple, easy approach to adding OpenMP, if we don't want to do much refactoring of the code, then it might be hard to get sufficient parallel coverage. So that's just an Amdahl's law argument inside the node. Okay, so whereas with the MPI code you had fully parallel code in the sense that you've got multiple processes all doing their own thing. In the hybrid code, you may have parts of the code where only one thread is executing, and the other cores are therefore idle for a bit. That's just this sequential code type of overhead that I talked about last time. But it's possible that this is more of a problem because we're working within the constraints of an existing parallel design. That's all we're trying to say here. Okay, other things. So the mixed implementation may actually require more synchronization than what you would need for a pure MPI, for a pure OpenMP version. If we assume that our MPI is not thread safe, and In MPI, the implicit point-to-point synchronization via messages may be replaced by barriers in OpenMP, which is actually might be more expensive. So that's maybe surprising, but talked last time that how expensive OpenMP barriers can be, and that a full OpenMP barrier across 64 threads might actually be more expensive than doing a halo exchange inside a node between 64 MPI processes. And this is part of the reason for this is because this kind of loose, point-to-point, thread-to-thread synchronization is hard to do in OpenMP. It's not well supported by any of the OpenMP synchronization primitives. Another thing to realize is that a lot of MPI codes are written in such a way as you essentially have communicators. So you do a bunch of computation, and then there's a phase where all the MPI processes communicate with each other, and then they go back to doing computation again, and so on. And so if you think about what's happening in a pure MPI code on one of these clustered systems, then the intranode messages, so messages which are going between MPI processes on the same node, those will often be naturally overlapped with the internode messages. So messages going between nodes across the network and messages going inside a node through shared memory can very naturally happen at the same time. But it turns out to be harder to overlap inter-thread communication with internode messages, and I'll give an example of why that is later on. And so we discussed last time, OpenMP codes can suffer from this false sharing phenomenon. So this is where we have cache-to-cache data transfers caused by multiple threads accessing different words in the same cache block. So MPI naturally avoids that because every MPI process has its own separate address space. So there's no way that two MPI processes can access neighboring words in memory, unless we're using MPI3 shared memory segments, of course. But apart from that, there's no way that MPI can suffer from false sharing. And then we have to worry about NUMA effects. So this really goes back to what I was talking about last time. So just to recap very quickly on that, so nodes which have multiple sockets are NUMA, and now we're also getting these chip designs where each socket has multiple NUMA domains as well. So basically each socket or each NUMA domain has its own block of RAM, and the operating system allocates the virtual memory pages to physical memory locations. So it has to choose. Every time the operating system allocates a memory page, it has to choose which socket or NUMA domain it's going on. And then there's this issue that the common default policy in Linux is this first touch idea. So it's allocated on the socket where the first read and write comes from. And that's clearly a sensible thing for MPI, but it's bad for OpenMP if we haven't done something pretty careful about our data initialization. In practice, what that really means is that most of the time, NUMA effects limit the scalability of OpenMP. And it's almost always advantageous to run at least one MPI process per NUMA domain rather than one MPI process per node. And so this just again, this will just come out in your experiments if you try to decide how many OpenMP threads per MPI process you want to run. Then you will almost always find that more OpenMP threads than you have cores in a NUMA domain is not going to be optimal. And as I hinted at before, we have issues about process and thread placement. So if we have NUMA nodes, then we essentially need to make sure that the MPI processes are spread out across sockets, and that the corresponding OpenMP threads are all running on the same socket as their parent process. This is largely under the control of the batch system, and if you're lucky, then the batch system on the machines that you're working on are correctly and well set up to cope with this. If it's not, then it can be a real problem to fix it as a normal user to try and get the process and thread placement correct. And it gets even more complicated if you're actually using hardware threads, virtual cores, hyperthreads, SMT, whatever you like to call it. If you're running more than one OpenMP thread per core, then the placement problem gets more complicated. And again, the default behavior in the batch system may not be what you want. It can be hard to figure out what the right settings are to get that right. Okay, any questions before I move on to talk about more about the practicalities of how we do this? Okay, so Eva is asking, what kind of instrumentation can be used for profiling such codes and exploring load balance problems? So most profiling tools will cope fine with hybrid codes. Okay. Yeah, so tools like Craypat, Scholastica, Map, all those tools will cope fine with hybrid codes. Interpreting the output, as ever, can be difficult, but most of the codes do support hybrid. Yeah. Okay. So let's think more about the practicalities of programming. So we can actually identify 4 different styles of MPI plus OpenMP programming, and these depend on when and how the OpenMP threads are permitted to make MPI library calls. So each of these has its advantages and disadvantages, which I'll talk through. And MPI has a threading interface which allows us as programmers to request and query the level of thread support that the MPI library provides. Okay, so these are the 4 styles. So the first one is called master only. So this is the simplest one, where all the MPI communication takes part in the sequential part of the OpenMP program. So that means that there's no MPI calls inside any parallel regions. Second one is called funneled. This is where all the MPI communication takes place through the same thread, which is the OpenMP master thread, but that could be inside parallel regions as well as outside them, as long as it comes from thread 0 in the parallel region. Third one is called serialized. So this is where only one thread at a time makes MPI calls. But this then becomes tricky because we now need to distinguish, if we have multiple threads calling MPI, we need to have some way of distinguishing the sending and receiving threads to MPI. And this has to be done through MPI tags or communicators. And then we have to start being a lot more careful about potential race conditions on the send and receive buffers. And then final style is multiple, where we allow MPI communications to happen simultaneously in more than one thread. So with the caveat that some implementations don't support that, and those which do may often not really perform very well in this style. The MPI implementations are getting better. There's been a fair amount of work done to try and improve the performance of MPI when we've got multiple threads active inside the MPI library. But in general, it's difficult to do, and it's not always that good. Okay, so just a schematic code to illustrate these. So master only, we would have potentially OpenMP parallel regions where we do some computation, and then the MPI communication happens in the master thread outside of parallel regions. And for funneled, now we allow communication inside parallel regions, but we have to restrict it to the master thread. So we might have the situation where all the threads do some computation, then they synchronize with each other at a barrier. The master thread does the MPI call. We synchronize again so that all the threads know that the MPI calls have completed, and then the threads can carry on doing some more work in parallel. And for serialized, well, there's a lot more options here, but for example, one thing that you could do for serialized would be to allow multiple threads to call MPI, but enclose the MPI calls inside a critical section, for example, so that we guarantee that only one thread at a time is ever inside the MPI library. And then finally, for multiple, anything goes. Okay, so we can have parallel regions where threads are doing computation and other threads are maybe doing MPI communications, and all that can happen at the same time. Okay, so I've already alluded to this idea that making MPI libraries thread safe is actually difficult. This is partly just for software engineering reasons. Implementing MPI is difficult. It's a bunch of there's a lot of code inside the MPI library, and that code is a lot of that code is quite complicated because it deals with has to deal with low-level network interfaces, but it also has to there's a lot of tricky implementation details to do with handling message queues and allowing allowing messages to arrive out of order and dealing with all that kind of stuff. As far as I'm aware, there is no MPI implementation that has really been designed ground up to be with thread safety in mind. They're all these relatively old implementations. So even OpenMP MPI is relatively old. Okay, it wasn't designed like this. So a lot of MPI implementations were either based on OpenMPI or some derivative of MPitch code bases. So neither of those were originally designed with thread safety in mind. So the thread safety features have to be retrofitted, and that means you have to do things like you either have to lock access to data structures inside the MPI library, or replicate them so you have a separate data structure for every thread. It's just all a bit horrible and nasty. So adding thread safety to MPI can add some significant overheads. So you don't necessarily want it there if you're not going to use it. And so for that reason, the MPI defines various supply an appropriate implementation. So it might only give you the thread safe, it allows MPI to only use the thread safe version if you ask for it, rather than have to use it all the time and potentially damage the performance when you're not using multiple threads. So the way this works in MPI is that you have a call called MPI init thread, which is a replacement for MPI init. Okay, so instead of calling MPI init at the beginning of your MPI program, you call MPI init thread instead. And this has two additional arguments. So basically, you pass in the level of desired thread support that you want, and then it returns back to you the level of thread support that's actually provided. Okay. And the levels of thread support that you can ask for are predefined in the MPI standard. So first one is thread single, which says, okay, I'm not using multiple threads at all. Second one is thread funneled, which says, okay, my MPI processes may be multi-threaded, but only the main thread is going to make MPI calls. Third one is serialized, says my MPI processes may be multi-threaded. Different threads may make MPI calls, but only one at a time. So I guarantee that I'm not going to make MPI calls concurrently from two distinct threads. And the final one is thread multiple. So multiple threads can call MPI without any restrictions. So you can see these sort of map on to the different styles of hybrid programming, except that both master only, in principle, both master only and funneled styles both require, in principle, MPI thread funneled. Okay. In practice, probably master only will work with thread single. So Jakob asks, if it is initializing MPI threaded with MPI thread single equivalent to just using MPI init? The answer is, well, probably yes. Okay, that's down to the implementation, what it does, but most likely yes. What I guess the question is, what is if you call MPI init, what is the default level? And I think you basically just don't know. Okay, that's down to the implementation. So these different levels are actually integers and guaranteed to be monotonic. Okay? So you can test sensibly. Okay, and I've already mentioned the second point. Okay, so yeah, but in principle, both master-only and funneled styles both require MPI thread funneled. And then you can also just ask, there's also an MPI query thread, returns the current level of thread support. So actually, in answer to Jakob's question, I'm not sure about this. I've never tried it. If I just call MPI init and then call MPI query thread, that might work in the sense that it would tell me what level of thread support I was getting by default with MPI init. But I'd have to go and check the MPI specification to see whether that was allowed. So either using MPI init thread or MPI query thread, it's sensible to have some error handling here. Okay, so essentially, if the provided level of thread support was less than what you asked for, then you probably want to take some sensible avoiding action and stop the program and say, okay, this isn't because bad thing. The level of thread support wasn't good enough for what I wanted to do. Therefore, things might, something bad might happen. So it's probably best if we just bail out now, rather than carrying on and producing some dodgy results. Okay, so let's think about the advantages and disadvantages of these different styles, because we basically have to make a choice here. So master only, the advantages is that it's the simplest version, the simplest style to write and maintain, because there's a clear separation between the outer, in other words, the MPI, and the inner OpenMP levels of parallelism. And because all the MPI calls come from outside parallel regions, we don't have any concerns about synchronizing threads before or after sending messages. However, there are some disadvantages, because it means that threads other than the master thread are necessarily idle during MPI calls. So while the master thread is doing MPI, then there's no possibility for the other threads to be doing anything, because they're not inside a parallel region at that point. There's also implications for locality here, because every time we pass a buffer to MPI, then that implies some reads and writes to that buffer, and so all the data that we're communicating via MPI is going to get passed through the cache where the master thread is executing. So it means that the master thread touches all the data that's getting communicated, with the consequent locality or data affinity implications. So it also means that actually inter-process and inter-thread communication can't overlap, because the inter-process communication is happening outside parallel regions, and any inter-thread communication via reads and writes to shared memory is happening inside parallel regions, and those things are separated in time. Another downside is that The only way that we synchronize threads before and after message transfers is by starting and stopping parallel regions, which have a relatively high overhead. And another important consideration is if we're using derived data types, actually quite a lot of the cost is actually in the packing and unpacking of MPI buffers rather than in the transfer of data across the network. So if we use, if we're sending non-contiguous data, then inside the MPI library, that is all being packed into a contiguous buffer before it gets sent across the network. And that packing process can be potentially quite expensive. And in this style, it means that only one thread can possibly participate in the packing. Okay, so just want to illustrate some of these points with a really simple example here. Okay, so have a loop that does some computation and computes values in an array A, and then basically doing a very so this is a one element, one-sided halo exchange. So it's probably the simplest thing you could possibly do is that each process sends AN to its neighboring process and receives A0 from its other neighbor. And then it carries on and does some computation with the things that it's received. Okay, so let's make that hybrid. Oops, my formatting's gone slightly awry here. Okay, so in order to keep the same global problem size, I increased the value of n on every process by the number of threads. Okay, so just to say, okay, I'm going to keep the same global problem size. So that means each MPI process is now handling more data, and then that's divided up between the threads. Okay, so basically just increase the data size and then parallelize each of the loops. And so what's happened? Okay, well, things that might be that you might not think about or too much, or is that we've had it to add an implicit barrier at the end. We've got this implicit barrier at the end of this parallel loop, and that's absolutely required because we have to close the parallel region anyway because we're in master-only style. But we have to in principle there is a data dependency here. The master thread needs to know that this loop has completed before it can send AN. And in the original MPI version, when we were doing these MPI sends and receives, then some of those messages were going between nodes, but most of them were actually probably going inside a node. Okay, so if we're just communicating if we just have a one-dimensional decomposition, communicating with our nearest neighbor, and we assign contiguous MPI ranks to a node, which is normally what MPI will do by default, then most of those messages were actually intranode messages, and then at each there's kind of one there's one internode message going at the end of the node, and those were all basically overlapped. Okay, but now that we've gone hybrid, the inter-thread communication is actually happening inside this loop. Okay, we will get some because AI -1 here was probably written by a different thread than wrote AI up here. Okay, the corresponding element of A. So the thread reading AI -1 is a different thread than wrote the same element up here. That means there's going to be some cache misses, and that's what what constitutes the inter-thread communication. Those cache misses actually occur inside this loop, and they don't overlap with these messages anymore. Okay, so that's master only. What about funneled? Well, this is still relatively simple to write and maintain. And there are the advantages over master only is there's now potentially cheaper ways to synchronize threads before and after message transfers. And also, it's now possible for other threads to do something useful, to do some computation while the master is inside an MPI call. So we can now potentially overlap thread with computation going on in other threads. Downsides, well, we're now getting a less clear separation between the levels of parallelism. We still have this problem of data affinity, where the master thread is touching all the data that's being communicated. We still can't get we still probably can't get inter-process and inter-thread communication overlapping. And we end up with this awkward asymmetry between threads, which doesn't sit very nicely in OpenMP. What do I mean by this? Okay, so if we want to try and do some overlapping here, if we want the master thread to do some computation, to do the message passing, and other threads to do some computation at the same time, then how do we arrange that in OpenMP? Well, for example, one thing we could do is just do a test. Okay, so if my thread number is 0, then I'm the one that's doing the MPI calls. Otherwise, go away and do some computation. But that means that we're restricted what we can do in this else clause here. Can't use work sharing loops, can't use OpenMP4 directives in there, can't use explicit barriers in there because both work sharing and explicit barriers require the participation of all the threads in the parallel region. So that's a bit awkward. And then we could also, another possible solution would be to do it with nested parallelism. So you could have an outer parallel region with 2 threads, and then the thread 0 in the outer parallel region does the MPI, and then the other thread in the outer parallel region spawns a new parallel region to do some computation. But then that becomes, you get some higher overheads from nested parallelism, and then it becomes awkward to synchronize between this thread and these threads down here. So yeah, this kind of asymmetry doesn't sit terribly nicely with OpenMP's work sharing constructs and synchronization mechanisms that require the participation of all the threads. Okay. Next up is serialized. So now it's what's the advantages of this? Well, it's now we now lose this asymmetry. Okay, so it's now easier for threads to compute with others in an MPI call, and we can also now start to take care of the data affinity problems. We can arrange for threads to communicate their own data. Okay, although threads don't formally own data, but threads threads can now communicate the data that they are reading and writing. So we can get some better affinity properties here. Downside, well, this is getting harder to write and maintain. It's more complicated. We have to take care of all the synchronization. It also means that we are probably splitting up our communications into more but smaller messages. And that may incur some additional latency overheads. Okay? So whenever you send an MPI message, there's a fixed cost to start the message off, and then a cost per byte to afterwards. Okay, so depending on, you have a fixed, basically it's a fixed cost plus some cost per byte. And if you split your messages up into lots of smaller messages, then you incur this fixed cost more often. But then now we run into this problem there. We need to be able to distinguish between messages which are coming from or destined to different threads in the same MPI process. Because as far as sources and destinations are concerned, MPI only deals with processes. So if we have multiple sending messages to another MPI process, then we have to have some way of working out which message is which in order that the right thread receives it on the other end. And well, it's possible to do that using tags, using the tag field in MPI, or using communicators, but neither of those is particularly nice or satisfactory mechanisms. Yeah, okay, so I think I've maybe said this, okay. Yeah, because a call to MPI received by any thread in an MPI process will match an incoming message from the sender. So to distinguish between them, we can use tags. But if tags are already in use for other purposes, this gets messy, because you just get one integer to use as a tag. So if you're already using tags for something else in MPI to distinguish between different types of message, for example, then you have to introduce some by hand encoding mechanism to encode both the original tag and the thread ID inside this integer. So it's nothing complicated. It's just messy and error prone and not very nice. The alternative is for different threads to use different MPI communicators. That's okay for simple patterns. So for example, if thread n in one process only ever commutes with thread n in another process, then we can have an MPI communicator for all the thread ends. So different MPI communicator for all the thread ends. But then even more complicated patterns get messy quite quickly. So even like simple halo exchange patterns get really quite difficult to handle with multiple communicators. And then finally, we have multiple. So the advantage of this is that, in theory at least, messages being sent and received by different threads can overlap in time. Though in practice, what's going on in order to enforce thread safety, the MPI implementation, they may actually be internally serialized. And this style makes it much more natural to solve the affinity problem. It's much more natural for threads to be able to communicate the data that they're reading and writing. And also we have fewer concerns about synchronizing threads, right? Because essentially we've handed that responsibility over into the MPI library to deal with. Downsides: harder to write and maintain. Again, as you can't necessarily guarantee that every MPI implementation is going to support this. And as I've said before, some MPI implementations don't perform well in this mode. Okay, so sum up. Okay. Hybrid programming is actually becoming pretty common practice in applications on large systems. I think so. On our previous system, so Archer was the predecessor to ARCHER2, unsurprisingly. We did an assessment at one time, and as far as we could, it was a little bit approximate, but as far as we could tell, around about 30% of the consumed CPU hours were from hybrid codes. And it's possibly going to become more important as the core counts go up. It might depend on better implementations of MPI thread multiple to really make it really efficient. It's not easy, okay? Achieving correctness is hard. You have to reason about race. You have to race condition buffers, which can be quite complicated. Getting performance is hard, just because performance tuning is hard in general. And then we have also these other considerations like optimizing the choice of how many threads per process we're going to run, and making sure that the thread and process placement on numerous architectures is correct. Okay, so does anybody have any more questions? Gianpaolo, go ahead.
So I was wondering if we initialize the MPI with serial funnel serialized, but then this is not reflected in the code. Does the compiler throw an error, or we will have like an error at runtime?
No. So if you, I mean, the main problem is if you write in multiple style and you don't request MPI thread multiple. Okay, that's the most likely scenario where something's going to go wrong. You will just get nasty, incomprehensible runtime errors, because what's going to happen is you're going to get race conditions happening inside the MPI library. So
I see. So it would be a mess to debug if
nasty messes. You'll get some. You could get any sorts of horrible failures. You might even not get a failure. You might just get wrong answers.
So
yeah.
Okay.
You really don't want to do that. It's no, there's no way that the compiler is going to check how you're using MPI in your OpenMP code. There's absolutely no way.
But maybe some profiling tool might help, to tell you.
Yes, possibly. I mean, sort of some debugging tool might give you some clues what had gone on. So give you a clue that it had died horribly inside inside the MPI library somewhere, maybe. Okay, but really, yes, you should. If you're going to use multiple style, then you really need to make sure you've requested thread multiple. And I say it's good to put this. It's good to put a check in as well to make sure that the MPI library really gave you thread multiple, and that you take some avoiding action if it didn't give you what you asked for.
I understand. Okay, thank you very much.
Otherwise, really horrible, nasty things can happen. Yeah.
Thank you.
from my experience, mostly it doesn't really, if you're not using multiple, then it really doesn't matter that much. Okay, it's unlikely that if you, if you're using serialized and you actually only asked for funnels, then you have a very good chance that that actually works. Okay. It's really multiple that's the problem. Okay, if you have where you have the possibility of multiple threads calling MPI at the same time, that's the thing that's likely to go wrong. All the other styles are just likely to work anyway, regardless of what you asked for. I'm not saying you should be careless, but you will you'll most likely get away with it. Okay, so I actually, for a change, got through that a bit faster than my timetable said. So I think we'll just take our break now, but then just come back and start the practical sessions when you're ready, and I'll be back by 11 o'clock to start answering questions if you've got any on the practicals. So please feel free, I should say, please feel free to do any of the practical examples in any order if you want. If you're not particularly bothered about the hybrid stuff, then you can. There are a couple of other exercises which are to do with looking at NUMA effects and bandwidth effects and cache and fault sharing type things. So please feel free to just move on to those or do whatever you like, basically. Okay, or if you didn't finish some of the exercises from Tuesday, then obviously feel free to carry on with those. So no compulsion to do anything or to do anything in any particular order.
Yes, you're muted. Yeah, okay.
Yeah, sure. Yeah, good.
Yeah. So is general question about hybrid MPI MP. So say I have an application which have a domain decomposed in 36 domain, and then I have an old MPI application which runs say I run MPI run NP36. So every decomposition is on one MPI rank, say. Mm-hmm. Now, I want to, I start, say, to refactor this application to run hybrid. So say now I would run MPI run NP2, and then internally every MPI rank takes care of 16 decomposition. So I was wondering, in the application, so once I decide how many MPI rank I want to run with, is there a way to change it inside the application? So say I want to start with 2 MPI ranks, and then at some point in the application I want now to go back to 36 ranks.
No. It's the simple answer to that. No, there's really no way of doing that. So in principle, MPI standard supports process spawning, so that you can create new ranks. But a lot of MPI implementations just don't implement it. And it's almost certainly doesn't work properly with batch systems.
Okay. So,
okay. So the simple answer is no, you can't do that.
Okay. No,
yeah.
I just wanted, because I started.
No, because that would be convenient if you want, at some parts, if you wanted to make some parts of the program hybrid and not others. But it's really all or nothing, I'm afraid. Yeah.
Okay. So I guess probably the best way to do it is separate this application in two. So run the first one with MPI2 and then MPI run and MP2 and then with 16. Stop the simulation, then submit another job with 36 ranks, for example.
Yes, I think you'd have to.
Because I mean, in my case, like the overhead would be like to write to disk, the partitions and then read them again. Or alternatively, or for example, if I run initially with okay, I guess it's the same question. Is if I initially run with MPI with 36 ranks, and then I have like some job of a specific rank is taken from a thread of another rank. I guess it's not possible as well.
No, I think is the answer.
Okay.
Yeah.
Okay. No, sorry about the.
Yeah, you're typically very limited as what you can do with sort of dynamically creating or destroying MPI processes. You're really stuck with whatever you start with is what you've got, and that's it.
And also always regarding this, say, okay, now the application is separated into two blocks. One, the first block which can run hybrid, and the second block which runs fully MPI. And say is submitted to a cluster. Do I need to submit two separate jobs, or with the same job I can run?
That depends a bit on your batch system, but because you'd be requesting, depends a bit on the batch system. You can probably have, it's probably okay to have, two separate MPI runs. It very much depends on how your batch system's set up. Okay, as to where does the control come from for the number of processes? Okay, because in some batch systems you can say MPI run and then give the number of processes there. In other batch systems that you specify that in a different way as part of the batch script. So it's very, very batch system dependent, I think, as to whether that works or not.
I see. Okay.
But most batch systems allow you to have dependencies between jobs.
Yeah.
So you can just two jobs, and the second one won't run until the first one's finished.
Yeah, it just I mean, not to lose the priority, so that once I submit a job,
once you've got the job running, you don't want to have to stop it again.
Yes, once I have the resources, just to mix and match, how to use them.
Yeah, I think you're gonna have to. What batch system are you generally using?
How I submit jobs? You mean the Slurm?
Is it Slurm?
Yeah, Slurm.
Okay, so I think it may just depend how it's set up as well. Whether you can, whether it's happy for you to specify the number of MPI ranks on the srun command, or whether it takes it from whether you specify the number of tasks for the whole job. Yeah.
Okay.
So you probably it's probably okay if you can specify the number of processes separately from the resource that you're requesting. Then it would work.
Yes. Okay. I never tried this.
I'm not entirely sure what would happen there.
Yeah. All right. Okay. I understand. Thank you very much for your answer.
Okay, I'll maybe go and have a dig and see if I can find a better answer for you.
Or for example, even thinking about Archer, just is out of curiosity, because if it's possible, because I mean currently the cluster where I'm working, for example, I specifies n CPUs per task on the on the submission job. So I don't know if it's possible to change it dynamically, like halfway to the script.
Yeah, that's a good question. I'm not sure I completely know the answer, but I'll try and find out for you. Yeah.
Okay, thank you very much. Thank you.
Yeah.
I think what you can do is because the question is, I mean, you can run the two SR runs, and each one can have a different configuration. Let's say you will need, I mean, in the script you will define the number of nodes, let's say 8, but later in SRun you can specify, okay, with these nodes I need CPUs per task equal 4, 8. Rather than specifying that at the beginning of the script with SBatch,
you can
there are two ways, either in the script at the beginning or in SRun. In your case, you will need to define it in SRun. Another way, in case that you want to submit 2 jobs, you can submit one job with one specification, one SRun, and the second job, when you submit, you can say that this job depends on the previous one. So for the scheduler would know, okay, I need to first run this job and wait until this job has run until the other one. There are different ways to which one maybe is best or worst. That's don't know.
Yeah. Okay, thank you very much. Thank you.
No problem. Also, the best way is to try now that you have access, to try different examples and see what works best for you. So.
Yeah, I'll give it trials in the next 2 weeks, as long as I have the access. So, yeah, thank you.
No problem.
Hi, everyone. Just very quickly before we take a lunch break, I thought I'd share some results from some hybrid OpenMP MPI benchmarks that I ran on ARCHER2 a while ago. And so what I'm showing here is the relative performance compared to the pure MPI version. So all these runs are on a fixed number of nodes. So everything is run on 8 nodes. So that's 1,024 cores. And then what I'm doing is just varying the number of, so I'm keeping the total number of cores I'm using fixed, and then varying the number of OpenMP threads per MPI process from 1, which is essentially pure MPI, up to 128, so I have just 1 MPI process per node and 128 threads. And so this is a relative performance. So if it's greater than 1, it means the hybrid version is faster than the pure MPI version. If it's less than 1, it means the hybrid is slower. So what you can see is that the different applications have different characteristics here, but for mostly the optimum number of threads per MPI process is typically either 4 or 8. So it's relatively small compared to the total number of cores that there are on a node. And for the most part, let's say, apart from Pennant, which is the purple line here, once I go beyond 16 threads per MPI process, then on the ARCHER2 nodes, each process is then spanning more than one NUMA region. So NUMA regions are 16 cores on this architecture. So for the most part, using more than more than 16 threads is generally a bad idea and gives you significantly worse performance. And using 128 threads per MPI process is generally awful. So you definitely can see some benefits. So it's typically between, maybe depends on the application, anything between 10% and 40% performance improvement from the hybrid version. Okay. Anybody have any questions want to ask before lunchtime? Okay, fine. In that case, thank you, and I'll be back at 2 p.m. UK time for the last set of lectures. I'll be talking about some of the more recently added features in OpenMP, and in particular the accelerating offloading stuff. So I'll give you a quick tour of that. We don't have any GPUs in ARCHER2, so can't let you have a play with it. But apart from that, I'll at least give you an idea of how it works and what it looks like. Okay, thanks everyone. I'll speak to you later.